The octahedron is the second most important shape in chemistry after the tetrahedron, and the octahedron is the most important shape in inorganic chemistry. We can represent the octahedron a number of different ways. One common way of doing it shows some resemblance to the trigonal bipyramid. So we could take a typical octahedral compound, sulfur hexafluoride, which is a inert gas, and we can represent the octahedron this way. One thing which this representation is useful for, it shows the fourfold symmetry. What it doesn't show well, though, is the fact that all 6 of the fluorine positions are identical in the octahedron. Let me show another way of representing the octahedron, which shows more clearly the name. The name octahedron means 8 faces, and each of the faces is going to be an equilateral triangle. So here's one of the faces. Here, for example, is the second face. So we can draw the various faces of the octahedron to make it look more like the geometric shape. So it has these 8 trigonal faces. Another way of representing the octahedron, which is often very, very useful, is to draw it as a 6-pointed star. So we draw it this way. What is particularly nice about this type of representation is that it highlights the threefold axis. And to show where the threefold axis would be on the left picture, we see one of the trigonal faces. So the axis would go through the face and come out the center of the opposite face. So that would be represented as an axis through the red point. And we can include the other constituents this way. Another thing which is useful is to recognize that in the octahedron, we can see that these 3 fluorines are connected to each other because they're on the same face. These 3 fluorines are connected to each other. We also want to keep in mind that these 2 particular atoms are going to be connected, as well as these 2. So some of these other connections aren't as obvious in this particular representation. And it's important for the student to get used to representing the octahedron in many different ways and seeing it represented in numerous different ways. So what's useful about this particular representation is that it makes it easier to see 2 of the distinctive and important symmetry operations of the octahedron. So it's the point group OH. One of the important symmetry operations that we can notice here is that if we rotate by 120 degrees, it will take this fluorine to that fluorine, this fluorine. So for the front face, it will permute the fluorines, so it'll look the same. The same happens with the 3 fluorines on the back triangle, the back face. So this molecule has the symmetry operation of C3. If we rotate clockwise, so we go in this particular direction, the molecule again look the same, so it has the symmetry operation of C3 to the -1. Now a more complex but related symmetry operation is found along the same axis. So here we have this particular axis here, which goes normal to one of the faces of the octahedron, is the following. So let's remove this. And this is going to be an improper rotation. We had seen already that for the tetrahedron, the high order rotation axis was actually an S4 improper rotation. And it turns out, likewise, for the octahedron, that the high order rotation axis is actually an improper rotation. And to see that, let's look at our diagram and notice what happens if we do a rotation by 60 degrees. So this is a C6. Now, if I do this rotation by 60 degrees, I notice that I will move this fluorine here 60 degrees, but it doesn't line up because this fluorine is behind the plane and this fluorine is in front of the plane. So one thing to keep in mind is, by perspective, this triangle is above the plane of the board and the triangle behind it is below the plane of the board. So when I rotate this fluorine by 60 degrees, it's going to be in this position relative to the axis, but it's going to be in front of the board. So it doesn't line up yet. The same thing happens with this fluorine. It's going to go in front of here, but near to the board. And this fluorine goes to this position, but in front. So the effect of my C6 is going to be to lead to a molecule that looks like this. So I notice that it does look different because rather than having a vertex pointing up, I have the vertex pointing down. So that is the result after the C6 operation. But then if I follow this up by a reflection, so then I reflect in the plane of the board, it's going to take all the fluorines that are in front, move them to the back, move all the fluorines that are in the back to the front. So the ultimate effect of that sigma H operation is going to give me back my original shape. So that tells me that the combination of a C6 and a sigma H is actually a symmetry operation of the group, and this is the S6 improper rotation. So we can visualize an improper rotation, and this is the high order rotation axis for the octahedron. When we start to substitute the octahedron, we get some interesting and different point group assignments. The simplest way that we can substitute our compound is to replace one of the fluorine atoms with another halogen. So let's replace it by chlorine. If I do that now, I no longer have the point group OH, because in an octahedron, I notice that all 6 positions around the sulfur are identical. Since they're no longer identical, I know that it can't possibly be the point group OH. Let's see what point group it's going to be. Well, one way I can represent the molecule is by using the 6-pointed star representation that I used previously. So let's see what this looks like. And we can think of this being the front face for the time being, and then the back face would be from that fluorine down to this one. We pick any set we choose, but this is the one I'm going to use right now. So that gives us chlorine here and then fluorine at the other positions. A useful result of representing the molecule this way is that it makes it quite clear that if I'm looking for an S6 rotation here, well, that would take chlorine, fluorine, not even worrying about where it's positioned, it's just the wrong atom. So I know right away I no longer have an S6. By the same reasoning, if I try to do a C3, it would cause no problem with the fluorines in back. It would take one fluorine into another. But in the front, it would take chlorine into fluorine. They're not the same, so therefore there is no longer a C3. So there's no S6, there's no C3. Let's see what other symmetry operations we have. Now, another way of representing the octahedron in this particular case, which would be useful, is sort of a top-down representation. If I look down from the top, kind of looking this way, I would see chlorine in the center, and then 4 fluorines at the corners of the square. Now, also know that what I don't see in this particular diagram, below the chlorine atom is going to be the sulfur and the fluorine. They're going to be along the same axis. Well, what I do see is along this particular axis, which would be noted in red here, this particular axis, is that I can rotate by 90 degrees. So if I rotate by 90 degrees in this direction, it's going to take each fluorine into the other. And the chlorine, the fluorine here and the sulfur are along the axis, so they're not going to be affected by the rotation. So it tells me I do have a C4 rotation. And the C4 is going to be my high order rotation axis. The other thing which you might want to look for at this moment, we look for C2s that are perpendicular. We look for C2s that are perpendicular to the C4. Possible locations would be along this particular axis. And what I would notice is if I do that, it's going to take fluorine into chlorine, so that doesn't work. And any other of the possible axes that I might want to try would suffer from the same defect. Now there is a C2 that goes along the same axis as the C4. So if I rotate by 180 degrees instead of 90, I will get a C2. There's no question about that. But the C2 and the C4 are not perpendicular. They're coaxial. So I still have a C group. I don't have a D group. What can I do next? Well, I want to look for mirrors. Again, I might imagine trying a mirror in the plane of the board. But if I did that, that would reflect chlorine into fluorine. They're not the same. So there is no mirror in the plane of the board. But there are mirror planes along here. So I take a mirror plane along the diagonals or along the X and Y axes, I would find 4 mirrors. And the mirrors, since they're not perpendicular to the high order rotation axis, must be vertical mirrors. So since I have C4 plus vertical mirrors, that tells me that this particular molecule, this SClF₅, belongs to the point group C4V. So this will be if I make a monosubstitution in my sulfur hexafluoride, and the substituent is an atom and not a group of some sort. So as long as it's an atom and I make a monosubstitution, no matter where I put the chlorine, remember all 6 positions are identical. So if I can replace any one of them, it makes no difference. I will still end up with the point group C4V. So therefore, be careful that if you see a representation of this molecule, you can see the chlorine placed at any one of the positions. By putting it here, it makes it much easier to see the point group symmetry, but your teacher or professor may not be so kind and may decide to trick you up a little bit by moving the chlorine around. So one of the things we want to do is not only be able to represent the molecule in different ways, but be able also to rotate the molecule in such a way that we can put it in a position that makes it as easy for us as possible to ascertain the symmetry. So now that we've done monosubstitution, let's look at the possibilities when we have disubstitution. And it turns out that there's only 2 ways to disubstitute our sulfur hexafluoride. So the first way to do it, so let's put the fluorines in here. I may omit putting the sulfur in the center, but we'll assume that it's always going to be sulfur. Let me add 2 chlorines. And the chlorines are going to be in opposite sides of the sulfur. So these are this is going to be the trans isomer. And I want to ascertain the point group symmetry for this particular molecule. And this representation makes it easier to see because along this particular axis is going to be my high order rotation axis. And I would notice that I can rotate by either 90 degrees, in which case I have a C4, or I can rotate by 180, in which case I have a C2, but both of those are coaxial. So I see that I have a C4. Do I have any other C2s that are perpendicular? Well, I might try looking for a C2, for example, along the x-axis. And let's see what we get if we do that. Well, the x-axis would be here. And I notice that if I do a rotation about this axis, it would take chlorine into chlorine, fluorine into fluorine. So I really do have a C2, and this C2 in red is actually perpendicular to my high order rotation axis. Since that's true, it tells me immediately I've gone from a C4 group to a D4 group. So we have a D4 group of some type. And now the only remaining question is, what type of D4 group is it? And to ascertain that, we want to check for mirrors. So the first mirror to look for, since we know along this particular axis is the high order rotation axis, we are looking for a mirror in the plane sort of the equatorial plane here. And we notice that we do because the 4 fluorines and the sulfur are all in a plane, so they're not affected by the reflection. The chlorine on top is reflected in the chlorine at the bottom. So I definitely have a horizontal mirror. So this tells me that the trans-substituted SCl₂F₄ belongs to the point group D4H. One thing which can make it easier to ascertain the point group symmetry of molecules like this is to notice that if I were to remove the chlorines, this would change the chemistry, but it won't change the point group symmetry. And I recognize that I have some sort of square planar molecule. We'd already investigated quite a few episodes back the point group symmetries of square planar molecules, and we had already noticed that those were D4H. So we can see here the presence of the chlorine, so long as I have either no substituents or the same substituents above and below, I'm still going to have D4H symmetry. So let's look at the other type of dye substitution, which we can perform on our octahedral molecule. In this case, we're going to put the substituents right next to each other. Since they are right next to each other on the molecule, this tells us that we have the cis isomer. So it would be cis-SCl₂F₄. And we want to ascertain the point group symmetry in this case. Well, if we try the same trick that we did last time to look for a high order rotation axis along this particular axis, we run into trouble because if we try to rotate by 90 degrees, it's going to take chlorine into fluorine. That doesn't work. If we try to go by 180 degrees, it's going to take chlorine into fluorine. So we notice that we have no interesting, non-trivial rotational axes along here. Do we have any other rotational axes? Well, if I look along the x-axis, so we go along this particular axis here, I notice that if I rotate by 180 degrees, I flip it over, I do have a C2. It's going to take chlorine into chlorine, fluorine into fluorine, fluorine into fluorine. So we do have a C2. And that turns out to be our high order rotation axis for the entire molecule. Do we have any other interesting symmetry elements? Well, we notice along this same line, so along the line and also going through fluorine and fluorine here, I can reflect the near side of the molecule into the far side, which tells us that we have at least one vertical mirror. And I also have a mirror in the plane, the equatorial plane of the molecule, in the plane of the fluorine, fluorine, sulfur, and 2 chlorines. In that particular plane is a mirror plane. It reflects fluorine on top into fluorine on the bottom. So that tells us that we have the identity, a C2, and 2 sigma V's. So therefore, the cis isomer has C2V symmetry. So we notice that depending on whether we have cis or trans dye substitution, will change the point group assignment of the resulting molecule. Substitution will change the point group assignment of the resulting molecule. The next important cases for octahedral molecules involve tri-substitution. So let's look at a case where we start off with what's at least formerly sulfur hexafluoride and replace, put several of these on here, and let's replace 3 of the fluorines with chlorine atoms. So we're tri-substituting with one particular new halogen. And one thing, so this is going to be SCl₃F₃. And it turns out, in this case also, there's only 2 distinct ways of arranging the substituents. In this particular case, let us notice that there's something interesting about the way that the chlorines are arranged, that I can draw a line from here to here, here to here, and then here to here. I notice that all 3 chlorines exist on the same face. So let me even draw it in our 6-pointed star diagram. And I'm even color coding the particular face to make it easier to see. And we notice that the corners of the closest face, we have the 3 chlorine atoms. And on the 3 corners of the far face, we have fluorine. So this is a particularly useful way of representing this particular isomer, because if we look along this particular axis, we notice quite clearly that if I do a 120-degree rotation, it's going to take chlorine into chlorine, chlorine and chlorine for the front face. So I see that it seems like we have a C3 rotation, at least for the front. Let's see what happens to the back face. Well, it's going to take fluorine to fluorine, fluorine to fluorine, fluorine to fluorine. So I do have a C3 rotation for the entire molecule. So C3 is actually a symmetry operation of the group. This representation also helps us find mirror planes. Now we might hope to find a mirror plane that's perpendicular to the C3. If there were such a plane, it would be in the plane of the whiteboard. And we can see right away that there is no such plane, because if there were, we notice that the chlorines are closer to us than the board, and the fluorines are essentially behind the board. So if we had a mirror plane, it would take the chlorines in front to chlorines in back, and there are, not only are there no chlorines there, there's no atoms behind there at all. So it tells us that we do not have any sort of a horizontal mirror. But we do have other mirrors. So for example, we have along this particular line, I can reflect the left side into the right side of our molecule, so we have at least one vertical mirror. We have another mirror going, that's kind of badly drawn there, as it goes to the fluorine. That's going to reflect the upper left with the lower right part of the molecule, and then I have one more if I draw carefully. Make sure to go through both the fluorine and the chlorine. Reflect the lower left with the upper right. So I have not only a C3, but I have 3 sigma V's, which tells me that this particular molecule belongs to the point group C3V. So I noticed that for this particular isomer, now, what do we call this isomer? Well, since the 3 substituents are all on the same face of the octahedron, we call it the facial, and we shorten that to fac, F-A-C. So F-A-C is for facial. And they're facial because they are all on the same face. Kind of like the song Face to Face. So this is one of the 2 possible isomers when we have tri-substitution. Let's look at the other isomer. There's only one other way to do this. So set up our octahedron. And in this particular case, we're going to put the chlorines along the waist, so to speak, of our molecule. And in this sense, I'm being kind of sloppy, but informal in the sense that we can think of the molecule as having a head, feet, and then this is the waist. Kind of anthropomorphizing the molecule, but that can be helpful. The more formal way of referring to the waist of the particular molecule is called the meridian. So this is the meridional or mer isomer of SCl₃F₃. So these are along the meridian. And we want to ascertain the point group symmetry of this particular molecule. So again, we can look at the 6-pointed star representations. Let's see what that would look like here. Let's pick this to be our front face. And we notice in this case we have chlorine and chlorine, but at the top vertex we have a fluorine atom. So let's put the fluorine there. And let's see what we have at the other positions. I know that one of the positions, the position behind this chlorine is a chlorine. So we recall that this position is connected to that position. So the other chlorine is going to be right here. And then the other positions are fluorine atoms. So this makes it clearer that if we try to do some sort of a C3 rotation, that there is none. Because for neither the front triangle nor the back triangle will this work, and it doesn't work. Do we have any other symmetry elements? Well, this diagram is not particularly helpful for it, but if we look at the molecule itself, we notice in this representation, if I look for a line that goes like this, so diagonally across the molecule, that if I do a C2 on this particular axis, it's going to take chlorine to chlorine, fluorine, sulfur, and chlorine along the axis so they're not changed. It takes the bottom fluorine into the top fluorine. So that means that this particular molecule does have a C2. C2 axis there. It's along a diagonal. It's not either the X or Y axes directly. We're looking for other symmetry elements. Well, again, along this line and then going through fluorine and fluorine here, there's going to be a mirror plane. And since it includes this C2 axis, it must be a vertical mirror. And then in the plane of the meridian, where the 3 chlorines and the fluorine reside, there's also a mirror plane because it reflects the fluorine at the top to the fluorine at the bottom. So we have, again, the identity, a C2, and 2 sigma V's. So that confirms for us that the mer isomer must belong to the point group C2V. So, but the 2 distinct ways of try-substituting it, for the facial isomer, the fac isomer, we have C3V being the point group. For the meridial, we have the mer isomer. The point group symmetry will be C2